Hello, welcome to our the beginning of our next unit. Today we're going to be looking at lessons 31, -1 and -2. We're going to be looking in these lessons at polygons and the angles that are involved in those polygons a little bit closer. By definition, a polygon is a closed figure, a closed plane figure, that is formed by 3 or more segments who intersect only at endpoints. Okay, there's a lot of vocabulary associated with these polygons that we want to kind of go through and talk about here, so that as we go through some of the information about the polygons, you'll be able to follow along a little bit easier. Each segment that forms a polygon is simply referred to as one of the sides of the polygon. The common endpoint of two sides is called the vertex. And a segment that connects any two non-consecutive vertices is referred to as a diagonal. So for example, on the diagram above, this would be considered a side. This point where they intersect is a vertex, and a diagonal can be drawn from any vertex, let's say vertex A, to a non-consecutive vertex. Now keep in mind, we can draw multiple diagonals in a polygon. Okay, a few basic names. Polygons are named according to the number of sides, which again will become very important as we start asking about some of the measurements of angles. We already know the majority of these, but just to kind of quickly go through them, a 3-sided figure is a triangle, 4-sided is a quadrilateral, 5-sided is pentagon, 6 sides is hexagon, 7 sides is generally referred to as a heptagon. 8 sides is octagon. 9 is nonagon. 10 sides is a decagon. And 12 sides is dodecagon. Just think of that as do being 2 plus decagon being 10. Now, anything after that we just refer to as n, and we simply call it an n-gon, which means that the number of sides could be up to 100 or more. When all the sides of a polygon are congruent, we call that equilateral. When all of the angles are congruent, it's called equiangular. In certain specific situations, we're going to have a polygon that is both equiangular and equilateral, so all sides and angles are equal. This is called a regular polygon. Now, if a polygon is not regular, we keep it nice and simple, and we call it an irregular polygon. Polygons can come in 2 forms. A polygon that has a diagonal, any diagonal that contains points outside of the figure is called a concave polygon. And a polygon where the diagonals don't contain any points outside the figure is called a convex polygon. Most of the rules that we're going to be looking at in this unit will refer to these convex polygons. So we have a couple of goals here. Our first goal today is to figure out what is the measure of the interior and exterior angles of any polygon. We want you to think about, in other words, what do all of these interior angles add up to each time? Okay, and we want to decide, is that going to be different for each different polygon? Is it going to be the same for different polygons, etc.? So we'll start this kind of exploration by starting with our smallest polygon, the triangle. We're going to pick one vertex, and we're going to draw diagonals from that one vertex to any other vertex. Now keep in mind, technically a diagonal goes to a non-consecutive vertex, so in this triangle, there's no real diagonals to draw. If we come down and as we fill this out, we're going to start filling in one of these tables. A triangle we know has 3 sides, and there's only one triangle that we can draw in this picture based on those diagonals. If we look at a quadrilateral, pick one vertex, and again, we'll draw all the diagonals from that one vertex to a non-consecutive vertex, and we can see that this 4-sided figure now has 2 triangles drawn, triangle 1, triangle 2. If we go to the pentagon, again, pick one vertex. We'll draw all the diagonals from that one vertex. So from here to here, from here to here. And those are the only diagonals that we can draw to non-consecutive vertices. Now we'll see that that five-sided pentagon now has three triangles. 1, 2, 3. Our hexagon, pick this one vertex, any of the vertices, and draw the diagonals to all the non-consecutive vertices. And we can see that this six-sided hexagon now has 1, 2, 3, 4 triangles. Okay? And then we want to kind of follow this on to what if it is an n-gon? So what if the number of sides is 7 sides or 8 sides or 100 sides? Notice the relationship between the number of sides and the number of triangles. Every time, if we take the number of sides and subtract 2, we're going to get that number of triangles. So if we follow that through, if it is an n-sided figure, we'll just write n, and we follow our pattern of subtracting 2, then the number of triangles would have to be n minus 2. Now, how does that help us find the sum of all of those interior angles? Remember that every triangle has 180 degrees. So if there's only one triangle, then there's going to be a sum of 180 degrees. If there's two triangles, however, or if there are three triangles, and each triangle is 180 degrees, we're going to have to take that number of triangles and multiply by 180. In a quadrilateral, then, the sum of the interior angles is 360. In a pentagon, if we multiply the three triangles by 180, that's 540 degrees. In a hexagon, if we multiply the four triangles times 180, that's a total of 720 degrees. And finally, in an n-sided figure, we'll do n minus 2 times 180 to come up with the total sum of the interior angles. So that leads us to our first formula, the polygon angle sum theorem. The polygon angle sum theorem states that if we want to find the sum of the interior angles of a convex polygon with n sides, we will simply take that number of sides minus 2 and multiply by 180 degrees. So a couple of examples where we're going to be using this theorem. If I say find the sum of the interior angles of a convex heptagon, we know that a heptagon has 7 sides, so we'll do n minus 2 times 180. 7 minus 2 times 180 is 5 times 180, and 5 times 180 degrees is 900 degrees. Now, if I said find the measure of each interior angle, and I tell you that it's a regular heptagon, remember that a regular heptagon means that all angles are equal. So if there are a total of 7 angles, then we'll take that 900 degrees, divide by those 7 angles, and that gives us approximately 128.57 degrees for each angle. Now keep in mind, this only works if it is a regular hexagon or a regular polygon where all the angles are equal. Okay? Find the sum of the interior angles of a convex 16gon. So without naming it, we do know that the number of sides is 16. Using our formula from above, 16 minus 2 times 180 is 2,520 degrees for our total. Keep in mind that is the total sum of the interior angles. If I want to find the measure of each interior angle, and we know that it is regular, then we can take that 2,520 degrees, divide by the number of angles. Remember that if there are 16 sides, then there will also be 16 angles. And when I divide 2,520 by 16, we get about 157.5 degrees. Now working backwards, we want to know how many sides does a regular polygon have if I tell you each interior angle. Well, think about what we did up above before we come back and do these problems. Up above, we determined that if we took the sum of all of the interior angles and we divided by the number of angles, that would give us the measure of each angle on the interior. Now, how do we find the sum of the angles? To find the sum of the angles, we did n minus 2 times 180. The number of angles was n. And now we are given the measure of each angle. So if we use this formula, I'm going to highlight this in green here. If we use this formula and I give you the measure of each angle, I should be able to set that equal to this to solve for the number of angles or the number of sides in the polygon. So back over here, we know that each angle is 108 degrees. We'll set that 108 degrees equal to n minus 2 times 180 divided by n. Remember, that's the same formula that we saw right down here. Now, when solving this, my recommendation would be that we write a proportion and we cross multiply. So I'll multiply 108 times n equals n minus 2 times 180. Then I'm going to distribute on this side. So 108n equals 180n minus 360. Since I have the variable n on both sides, I'm going to need to get that on the same side. So if I subtract 180n, that will give me, let's see, that's going to be negative 72n equals negative 360 degrees. And if I divide by negative 72, n will be 5 sides. So on a problem like this one where we're working backwards, this formula, I'm going to highlight this formula for your notes, this formula is going to be key. How did we find the measure of each angle in a regular polygon? We took the sum of the angles, n minus 2 times 180, and we divided by the number of angles, which is the same as the number of sides. Our last, almost last example, one of our last examples of the measure of the interior angles in this hexagon. We want to find the measure of each of these interior angles. Now, I first want you to note that it is not a regular hexagon, meaning that the angles are not all the same. The first thing we need to do is figure out what is the sum of all of the angles. Okay, to find the sum of the angles, we'll do the number of sides minus 2 times 180. In a hexagon, there are 6 sides, so 6 minus 2 times 180 is 720 degrees. What that means is that all of these angles, if I was to take all of these interior angles and add all of these together, it should equal this 720 degrees. So I'm going to write an equation. My first angle, angle A, is 2A plus angle B, 5A, plus 4A, plus another 5A. Let me slide this down. Plus 3A plus 5A equals 720. Let's make sure we have all the angles here. This is angle A, B, C, D, E, and angle F for a total of 720 degrees. And when I add all of those like terms together, we get a total of 24A equals 720 degrees, which makes A 30 degrees. Now it actually says find the measure of each angle. So we actually need to go back and determine what each of these angles are, knowing that A is 30 degrees. So for angle A, 2 times 30 is 60, 5 times 30 is 150, 3 times 30 is 90, 5 times 30, 4 times 30, and another 5 times 30. Here's a second example of the same type of process. Find the measure of each interior angle of this pentagon. First, you want to find the sum of all of those interior angles. That's just n minus 2 times 180. Since it's a pentagon with 5 sides, 5 minus 2 times 180 is 540 degrees. And from there, we can set up an equation where we add together angle A plus angle B plus angle C plus angle D plus angle E, and it will equal the total of 540 degrees. Add all your like terms together, 2x, 3x, 10x, 19x, and 24x. Then we will add our 3 plus 1, that's 4, 9, minus 1 is 8, plus 4 is 12, equals 540. And when we solve this equation, we find that x is 22 degrees. Now, again, it does say go back and find the measure of each interior angle. So if we go back and plug 22 degrees back in, I'm not going to find all of them, but we can find the measure of each one by plugging in that 22 degrees. So this angle E here would be 114 degrees. The last thing I want to talk about, class, are the exterior angles. An angle that is formed by one side of a polygon and the extension of that consecutive side is referred to as an exterior angle. So in these diagrams, what we want to do first is find all the exterior angles. The first exterior angle would be this angle right out here. If the interior angle is 99 degrees, then subtracting that from 180 should give me an exterior angle of 81 degrees. And I can do that same process to find all these exterior angles. 180 minus 33 is 147. 180 minus 48 is 132. Over on this side, we're going to have 5 exterior angles. 180 minus 69 is 111. 180 minus 137 is 43. 180 minus 125 is 55 degrees. 180 minus 70 is 110. And 180 minus 139 is 41 degrees. And on our last figure, our hexagon, we'll have 6 exterior angles. 180 minus 105 is 75. This one will be 57. This one is 70. This one is 25. Here's another 70. And this one is 63. Now, what we want to look at is the sum of those exterior angles. So if we go back and in each diagram, add together all of those exterior angles. In our triangle, our exterior angles were 147, 81, and 132. And when I add those 3 together, I get a total of 360 degrees for the exterior angles. If I do the same thing on the next polygon, we'll take our 111 plus 43 plus 55 plus 110 plus 41. And if I add all those together, I get 360 degrees. And on our last one, our hexagon, if I add together 63, 75, 57, 70, 25, another 70, 1, 2, 3, 4, 5, 6. There's my 6 angles. If I add those together, I once again get 360 degrees. As we can see with just these 3 examples, there is a relationship between the exterior angles in a polygon, and that's what we call the polygon exterior angle sum theorem. What this one tells us is that the sum of the exterior angles of any convex polygon with n sides is always 360 degrees. So the nice thing with the exterior angles is that we don't have to find the sum. We know what the sum will be every time. When we start answering questions then, think about what it's asking. Find the sum of the exterior angles of a convex 20gon. We know that in every case, the sum of the exterior angles will always be 360 degrees. Now, if it says find the measure of each exterior angle, and we know that it is a regular 20gon, Remember that regular means all angles are equal. So if the sum of the angles, we'll take the sum, we'll divide by the number of angles. Now remember, the sum is 360 degrees, and a 20gon is going to have 20 angles. So 360 divided by 20 is going to give us 18 degrees for each angle, each exterior angle. And then finally it says find the measure of each interior angle of a regular 20gon. We can actually do this two different ways. Our first method would be, we know that the interior angle plus the exterior angle added up to 180. That's how we found the exterior angles the first time through. So if I'm looking for the interior angle, but I know that the exterior angle is 18 degrees, then I could set up this equation and find out that the interior angle is 180 minus 18, which is going to be 162 degrees. The second method would be going back to what we learned about the interior angles. We could first find the sum of all the interior angles by doing n minus 2 times 180. If this is a 20gon, we'll be doing 20 minus 2 times 180, and that's going to give us a very large 3,240 degrees total. Then divide that by the number of angles, and that gets us right back to that 162 degrees. Find the number of sides. So once again, now we're working backwards because now I'm asking you to find the number of sides. And remember that the number of sides will always equal the number of angles. They will be the same. It is a regular polygon, and we know that the exterior angles each measure 4 degrees. Well, when working with exterior angles, we know that if we take the sum of the exterior angles, which is always 360, divide by the number of angles, that will give us the measure of each angle. So if I do 360 divided by the number of angles, that should tell me the measure of each one. Once again, set up a proportion and cross multiply. This would give me 360 equals 4n. If I divide both sides by 4, the number of angles is going to be 8. So that means that there were 8 angles, which also means that there were 8 sides, which means that this was an octagon. Find the number of sides of a regular polygon whose interior angles each measure 135. So now we're going back to what we know about interior angles. For interior angles, we will have to find the sum of the interior angles, divide by the number of angles, and that will give me the measure of each angle. But with interior angles, the sum is not always the same. So with interior angles, we have to find the sum, we have to do n minus 2 times 180. We're going to divide by the number of angles, which is still n, and that should give me the measure of each angle, which we knew here was 135 degrees. And again, if we cross multiply, set up my proportion, I'm going to multiply these together. That's 135n equals, and then multiply this times 1, and minus 2 times 180. I'll distribute, so 180n minus 360 equals 135n. Since I have n's on both sides, I want to get all those n's to the same side. 135 minus 180 is going to be negative 45n equals negative 360. And if we divide by negative 45, n is going to be 8. I just realized that I made a mistake on example 7. I was looking at the wrong example. When we did 360 divided by 4, that's actually going to be 90 sides. I apologize. I was looking at the answer from the one below it. I'm going to skip our last example and then just take a moment to summarize what we've seen so far. We know that the sum of the interior angles can be found using the formula n minus 2 times 180. We know that if it is a regular polygon and we want to know the measure of one angle in that regular polygon, we can take the sum of the angles, divide by the number of angles, and that will give us the measure of each angle. So this is what we have to use when we are dealing with interior angles. Now, we also learned that if we are working with exterior angles, we know that the sum of all of the exterior angles is always 360 degrees. If we have a regular polygon and I want to know the measure of one angle, all I need to do is take that 360 and divide it by the number of angles or the number of sides to get the measure of each angle. So there are different rules for interior versus exterior. Make sure you pay attention to if you're being asked to find the sum, like in these cases, or if you're being asked to find one specific angle, like in these cases. So as you're going through and trying some of your homework problems, pay very close attention to what type of angles you're working with and what the question is asking you to